All right, I was right there finishing up in the last video. So hopefully this makes sense where I'm leaving off. That if the snow machine ended at t equals 10, what we can use is that same formula that we had from before to figure out how much snow is on the mountain. And this is what I was talking about before, that sometimes they're asked to find a formula but not to actually solve it for the K value when the snow would be all melted. So I hope this makes sense, because at that point we're done adding snow. So we figure out how much snow is on the mountain, and then we continue that. We're going to take away the melting amount as the integral from 10 until K, until we're all the way down until we're equal to 0. Now some people are a little bit more strategic about this, and what they'll do is they'll write 183.193 is equal to this piece. I'm trying to highlight. And the reason why that works is because you can add that over. And basically you want to see where they undo each other. How the amount of time it would take to undo that. Hopefully now I've justified well enough why that is your final answer. So moving on to the next piece of the notes. I believe these are online, so if you want a different explanation, you can at least see the answers. So what we have is the rate of fuel consumption in gallons per minute recorded during an airplane flight. Twice differentiable, strictly increasing, that's important. It's only increasing. The graph of R in the table selected values of R of T. Notice that the units are in here as well, gallons per minute, so you know that R of T is a rate. So use the table from the data from the table to find the approximation of R prime of 45. So we're looking at about these values. So I would just quickly mention R prime. I would just use the numbers. You don't have to write out that you're doing R of 50 minus R of 40. Which happens to be 40 over 50 minus 40. It's a quick difference quotient to say, okay, well, we have 15 over 10, which is 1.5 if you wanted to, if this is a no calculator question. And because it's R prime, it's a rate of a rate, then it makes sense that we are at gallons per minute squared. Something just like that. So part B, the rate of fuel consumption is increasing fastest at t equals 45. What's the value of R double prime of 45? Well, a quick explanation for it is using the mean value theorem, that if we're increasing the fastest, then what that means is that R prime is a max. Well, where do our max occur? Well, that implies that the derivative of a max is equal to 0. Now, I quickly just pulled up the answer key and how it just talks about because R prime has a max, then the second derivative must equal 0. Part of the reason why it must equal 0 is because the derivative does exist. If anybody wants a clarification on that. With this being a 2003 test, I feel like there's enough questions that one would be a little bit, it would be like a plus standard, so to speak. As you look at part C, we're approximating the integral using a left Riemann with 5 subintervals. So as I'm looking at, there's 1, 2, 3, 4, 5. Yep, it looks like we have enough data to do this. But notice that the width changes. So we're doing 30 for the first width and then times 20. And then the next width is 10 times 30. The next width is 10 times 40. The next width is 20 times 55. And then the last one is 20 times 65. I don't really want to go, slide down and do all the arithmetic. I think I'm actually just going to go back to the answer key since I already pulled it up to show you the work. Now I pointed it all out, and yes, this is a no calculator test. And this is like the 7/8 rule. If 7 of these 8 numbers are correct, or 9 out of 10, they'll probably give you full credit. Now, why is the approximation less than? Well, remember earlier we talked about a strictly increasing function. So let me go back to that. And we did the left Riemann sum. I think it'd be really easy if you just wrote right on the graph. Like, look at all these left Riemann sums. We're below the curve everywhere. These are terrible rectangles, by the way. But anyway, definitely an under approximation if we're only increasing with our left Riemann sums. And then for part D, explain the meaning in terms of fuel consumption, explain the meaning of this. We just talked about in terms of, and indicate the units of measure. I'm just going to, again, go back to the answer key. So total amount of fuel is in gallons. So notice the unit there. Versus the average value of fuels in gallons per minute, because it's now a rate when we have it written that way. So feel free to Google the 2003 AP Calculus AB scoring guidelines. You can find this, and you can get a, maybe re-reference this problem as we move forward. And then just another quick problem. I don't have the answer key to this, so I'm going to try and keep this simple, straightforward, to the point. So as we have 5 subintervals from 0 to 30, it makes sense that we're doing 6, 6, 6, 6, and 6. So that's 5 times 6 will get me to 30. And the midpoint Riemann sum are these values. So if I were doing this problem, I would actually just factor out that 6. But don't forget about that 1/30th either. 1/30th times 6 times, and then add together these values. 7.5 plus 12.5 plus 13.5. There we go. And what's the correct units? Well, it's a rate. So it's sticking with meters per second. And what's the meaning of this is that's the average value. So it's the average velocity of whatever this problem is doing throughout t equals 0 to t equals 30 seconds. So the average acceleration, because we're given the clues with velocity, would be doing v of 18 minus v of 6 over 18 minus 6. So we can figure that out. 14.1 minus 12.5 over 12, and with a calculator, without a calculator. And the correct units is average acceleration would be meters. So I don't know the answer, per second squared. So as we look at the next one, find an approximation for v prime of 6. All right, well, it's up to you if you did this. You can either do the average value between these two, or these two. And then because it's the approximation of v prime of 6, we are still in meters per second squared. So what does this value represent? Is the approximation for the acceleration of the particle, or whatever the object is, at that moment. So is the speed increasing or decreasing? Remember, we're going through all of our processes. If, well, because velocity is positive here, and it looks like we're increasing throughout no matter what. So acceleration will also be positive. Then, because they're the same sign, so V and A are the same sign, we have a speed is increasing. Because no matter what values you do, we are increasing throughout that interval. And then here's another one where we're doing the integral from 3 to 9. This time we're doing left-hand approximation. That's your left Riemann sums with 2 subintervals. Use this value to find the position of the particle at t equals 3 seconds. really wish I had an answer key on this one, where, you know, you're I guess we don't have. Oh, I see. Here's your clues. So what we could do is, once you practice doing your left Riemann sums of doing the integral of this, so the integral of 3 to 9 of b of t dt would equal b of 9 minus b of 3, and you can replace b of 9 with 60, and then solve for b of 3, and whoops, nope, that should say p of 9 and p of 3. Sorry about that. And when you solve for p of 3, whatever this answer is just going to be in meters. I have confidence because this is mostly review. I'm just kind of summarizing these things. But write down your questions. See if you understand, and bring them to class so then I can answer them. But you should be ready for the homework. We've reached the point where I think I have confidence that you guys can figure these out. Whoops.